Hey, what's going on? We are looking at acids and bases in this unit. Here we see the definitions for the Arrhenius acid and base. An Arrhenius acid is a substance that when added to a solution increases the hydrogen ion concentration. You can see here hydrochloric acid, when dissociated in water, will increase the hydrogen ion concentration in the solution. Down here you see an Arrhenius base is defined as a substance that when added to water will increase the hydroxide ion concentration into the solution. Sodium hydroxide, whenever it dissociates, you can see, now has released hydroxide ions. So by definition, in order for it to be an Arrhenius acid or base, it has to increase the ion concentration in the solution only. Later, Bronsted-Lowry came up with a new definition because there were examples of substances that were acids and bases but did not fit the Arrhenius definition. So a Bronsted-Lowry acid is anything that donates a proton or an H+, not to the solution, but to another compound or a base. So we can identify HCl as the acid because we can see the proton, the H+, is leaving when it dissociates, but not going into the solution, instead being accepted by the base. A Bronsted-Lowry base is anything that accepts the protons, so here NH3 would be our Bronsted-Lowry base, and it becomes NH4+, and our chlorine is now here alone without the hydrogen. So you can see the difference here. The proton is either accepted or released, not into the solution, but into the substance itself. So whenever we look at the practice worksheet that you see here, we could see what we need to know to identify these as Arrhenius or Bronsted-Lowry. When it comes to the acid, you really can't distinguish between the two, but here with sodium hydroxide has OH ions that will be released, making this an Arrhenius base as the OH would dissociate and enter the solution. NH2, you may realize, has an ability to absorb a proton or accept a proton, making it NH3+. Because it accepts a proton, it's a Bronsted-Lowry base. You may recognize this as an acid. It's polyprotic with 3 hydrogens. Phosphoric acid is clearly an acid, and like I said, you can't really distinguish between Arrhenius or Bronsted-Lowry. Hydrobromic acid is an acid. Calcium hydroxide, when dissociated, releases hydroxide ions into the solution, making it an Arrhenius base. And of course, water we know is amphoteric, which can act as both an acid or a base. When it comes to determining a strong acid from a weak acid, a strong acid will completely ionize or completely dissociate, whereas a weak acid only partially dissociates. So you're going to see some overlapping with pH. Sometimes a weak acid may have a stronger pH, a lower pH than a strong acid, but what determines whether it's strong or weak is not necessarily the concentration, but its dissociation. This is acetic acid. You're going to hear a lot about this. This is the formula for acetic acid. This is the primary one you'll see, but you may see it written as either one of these two as well. Overall, it does have 2 carbons, 4 hydrogens, and 2 oxygens, and it's the main component of vinegar. You can see the structure here for acetic acid, and it is an acid despite seeing this OH here, because it's going to only dissociate releasing this H ion into the solution. So the same thing will happen here. This is what makes it an acid, this hydrogen ion that can break off and then will release either to the solution or possibly to another substance. We see when acetic acid is added to water, we can clearly identify that it is truly the acid because this hydrogen ion is released and donated to the base in this case. So here's our acid. Because this accepted the proton, this is the Bronsted-Lowry base. And overall, whenever acetic acid is introduced to water, we see a change in concentration. We're essentially diluting the acetic acid. So if we think of molarity as the number of moles per liter, because the volume of the water is increasing, the overall molarity will decrease. So the concentration of hydrogen ions when acetic acid is introduced to water will actually drop. Given the relationship we know between hydrogen ions and hydroxide ions, if the hydrogen ions decrease, then what must happen to the hydroxide ions? Well, in this case, they would increase. We see the relationship, for example, in the formula that tells us pH plus POH equals 14. If the pH were to change one way, let's say the pH went up, then the POH would have to go down. Now, when we look at the structure of acids versus bases, and we need to know how many moles it's going to take to neutralize each of these, it all depends on whether the acid is polyprotic or not. Here we see it is polyprotic, releasing 2 hydrogen plus ions, either to the solution or to the substance. However, the potassium hydroxide, when it dissociates, only releases 1 hydroxide ion into the solution. So, how many moles of each would we need to neutralize? Well, if we had an even ratio, you could see that the ratio 2 to 1 would not satisfy this. So overall, for every 1 mole of H2SO4 we would need 2 moles of KOH to balance itself out, allowing it to be neutralized. Alright, so that's the video. Hopefully you all do well on today's test and that this helps. Thanks.